right? And we've talked a lot about using generative AI to produce new sentences, to produce new images, and so on and so to understand images, all these kind of different things. And the idea was that if we look at enough pairs of images and text, we will learn to distill what it is in an image into that kind of language. So the idea is you have an image, you have some text, and you can find a representation where they're both the same. The argument has gone that it's only a matter of time before we have so many images that we train this on, and such a big network and all this kind of business, that we get this kind of general intelligence, or we get some kind of extremely effective AI that works across all domains. Right? That's the implication. Right? The argument is, and you see it a lot in the sort of tech sector from some of these sort of big tech companies who, to be fair, want to sell products, right? That if you just keep adding more and more data, or bigger and bigger models, or a combination of both, ultimately you will move beyond just recognizing cats and you'll be able to do anything. Right? That's the idea. You show enough cats and dogs and eventually the elephant just is implied. As someone who works in science, we don't hypothesize about what happens, we experimentally justify it, right? So I would say if you're going to say to me that the only upward trajectory is going to, the only trajectory is up, it's going to be amazing, I would say go on and prove it and do it, right? And then we'll see. We'll sit here for a couple of years and we'll see what happens. But in the meantime, let's look at this paper, right, which came out just recently. This paper is saying that that is not true, right? This paper is saying that the amount of data you will need to get that kind of general zero-shot performance, that is to say performance on new tasks that you've never seen, is going to be astronomically vast to the point where we cannot do it. Right? That's the idea. So it basically is arguing against the idea that we can just add more data and more models and we'll solve it. Right? Now, this is only one paper, and of course, your mileage may vary if you have a bigger GPU than these people and so on, but I think that this is actual numbers, right? Which is what I like, because I want to see tables of data that show a trend actually happening or not happening. I think that's much more interesting than someone's blog post that says, I think this is what's going to happen. So let's talk about what this paper does and why it's interesting. We have clip embeddings, right? So we have an image, we have a big vision transformer, and we have a big text encoder, which is another transformer, a bit like the sort of thing you would see in a large language model, right? Which takes text strings, my text string today, and we have some shared embedded space. And that embedded space is just a numerical fingerprint for the meaning in these two items. And they're trained, remember, across many, many images, such that when you put the same image and the text that describes that image in, you get something in the middle that matches. Right? And the idea then is you can use that for other tasks, like you can use that for classification, you can use it for image recall. If you use a streaming service like Spotify or Netflix, right, they have this thing called a recommender system. A recommender system is where you've watched this program, this program, and this program. What should you watch next, right? And you might have noticed that your mileage may vary on how effective that is, but actually I think they're pretty impressive for what they have to do. But you could use this for a recommender system, because you could say basically, what programs have I got that embed into the same space of all the things I just watched, and recommend them that way, right? So there are downstream tasks like classification and recommendations that we could use based on a system like this. What this paper...
All right.